The triple bond is electron-rich. Alkynes also undergo electrophilic addition, but are much less reactive than alkenes. This would seem like a paradox, given that alkynes have more electrons in its triple bond than alkenes. However, explanations exist for this phenomenon. First, the pi electrons are more tightly bound due to the sp character of the bonding orbitals. Thus, they are made less available for interactions than the pi electrons in alkenes. The second is that the vinylic carbocation, presumably formed by the addition of the electrophile, are known to have low stability. In fact, it may even be proposed that they do not form at all. Hence, the energy of activation for the formation of this carbocation is considered to be higher compared to the formation of other carbocations. Hydrohalogenation occurs in alkynes, and given that alkynes contain two pi bonds, hydrohalogenation may occur once or twice depending on the molar equivalent of the added hydrogen halide. This type of addition follows the Markovnikov's rule and gives geminal dihalides. So in the first addition of the hydrogen halide, you expect to get a halide, in this case bromine, attached to the carbon with less hydrogens. Another equivalent of HBr will enable the attachment of another bromine atom to the same carbon where the initial bromine is added. When two bromine atoms are attached to the same carbon atom, we call this relationship as geminal or gem. So this is a geminal dibromide, as opposed to vicinal, where the groups or atoms are attached to carbons that are right next to each other. A controlled amount of hydrogen halide may be generated in situ by the mixing of an acid halide, in this case shown here is an acetyl halide, and alumina. Alumina cannot be dried completely, so water remains on the surface of this material. Water reacts with the acid chloride to form the carboxylic acid and an equivalent amount of HCl. So if I use a specific amount of my acid chloride here, let's say 1 mole of acid chloride, it is expected that I will produce 1 mole of HCl. A controlled amount of acid chloride can be used to produce a controlled amount of the hydrogen halide. Similar to alkenes, anti-Markovnikov addition of HBr occurs in the presence of peroxide. In the same way, if you control the amount of the hydrogen halide, the addition can be once or twice. If you use an excess of hydrogen bromide in the presence of peroxide, then a geminal dibromide is expected. Only that the reduced selectivity is in the opposite sense, that of the typical hydrohalogenation reaction. Acid-catalyzed hydration also occurs in alkynes, but they are much harder to do. This process requires sulfuric acid and mercuric sulfate in the presence of water. This hydration reaction will produce this compound. Here you have a double bond, the ene, and the alcohol, which is the ol. So you have an enol in this case. Now enols, or vinyl alcohol, rapidly rearranges to a keto form. This compound is acetone, which belongs to the ketone family. As you see here, the difference between the keto and the enol form is the position of the hydrogen and the double bond. Here the double bond is in between two carbons, and here the double bond is between the carbon and the oxygen. The formation of the keto form is favored because the double bond between carbon and oxygen is stronger than the double bond between two carbon atoms. The process in this rapid interchange between these two constitutional isomers is called keto-enol tautomerization, and these two compounds are tautomers. We must take note that they are not resonance structures. In resonance structures, only the pi and lone pair of electrons are moved. The connection between atoms are retained, but here, the hydrogen is transferred from this oxygen to this carbon. Now, how does keto-enol tautomerization occur? It's not that the hydrogen is directly transferred from this position to this position. It's too far away for that to happen. It occurs in a multi-step process, often requiring an acid or a base. Here, in the presence of an acid, this double bond will obstruct this proton to form this structure with a positive charge at this carbon. The lone pair will form the double bond, and the hydrogen that remains will be taken by a water molecule to produce this keto form. And so, when you do hydration of an alkyne, they will form an enol structure first, but this will ultimately end up as a keto form. If you wish to have a product with reverse regioselectivity than the hydration reaction, you can use hydroboration-oxidation. As you remember, this is the addition of borane followed by oxidation with hydrogen peroxide in the presence of a base. Thus, when you subject propyne to hydroboration-oxidation, you will produce this enol with anti-Markovnikov selectivity. This enol will ultimately be converted to an aldehyde, in this case as a terminal alkyne, and rearrangement to the keto form is expected. Thus, if you compare it to hydration, the double bond occurs at the terminal carbon. This is an aldehyde. It is also possible to do halogenation, or the addition of chlorine or bromine to the triple bond. Similarly, this halogenation can occur once or twice, depending on the molar equivalent of the halogen molecule. The addition of one molar equivalent of chlorine or bromine results in anti-addition and yields a trans-dihaloalkene, reflecting the anti-addition that was previously described for alkenes. The addition of another equivalent or an excess of the halogen results in the formation of a tetrahalide. The sp3 hybridized carbon is electronegative, and with this, the terminal alkynes are weakly acidic and yield an acetylide or alkynide upon proton abstraction. The pKa of acetylene or ethine is about 25, and if you have a strong base, it is possible to remove this proton. Reagents that can form alkynide include silver nitrate in ammonia, or we say ammoniacal silver nitrate, or silver nitrate in alcohol, or alcoholic silver nitrate. Other common reagents include sodium amide and lithium amide. Hence, if you react sodium amide with propyne, what happens is an acid-base reaction. Given that sodium amide is the conjugate base of ammonia here with a pKa of 38, and propyne has a pKa around 25, then we can say that propyne is a stronger acid, which will react with a stronger base. These two reagents are expected to react favorably to form the alkynide. If silver nitrate is used in the presence of ammonia, a similar reaction is expected to produce the silver alkynide. The alkynides are very important reagents in organic chemistry. They are nucleophilic, and hence if you react it with a compound such as ethyl iodide, the high electron density present here can be attracted to this partially positive carbon and kick out the iodine atom. In such a case, a new bond will be formed and a longer alkyne will be produced. This is one of the many important ways in creating new carbon-carbon bonds. Now to reduction. Alkynes can be reduced completely by catalytic hydrogenation in the presence of metal catalysts such as platinum, palladium, or nickel. This 2-butene here will be converted directly to butane in the presence of these reagents. If you wish to have only partial reduction, a Lindlar's catalyst is useful. Lindlar's catalyst contains poisoned palladium or palladium in calcium carbonate. Because this catalyst is poisoned, the reduction stops when the double bond is formed and does not go further. Now, given that the hydrogen is adsorbed at the surface of the metal, it adds only to the same side of the triple bond. Thus, the result of this reduction is a cis-alkene. The catalyst may be poisoned by lead salts such as lead acetate or lead oxide, quinoline, and others. Another possible reagent for the formation of cis-alkenes is nickel boride, or known by the code P2, and this will also give cis-alkenes. If transalkenes are desired, you may use dissolving metal reaction. This is sodium or lithium in ammonia or amine solvents at low temperature. This reaction leads to transalkenes. The mechanism here follows a free radical process. Oxidation of the triple bond can occur via ozonolysis. The difference for ozonolysis of the triple bond is that there's no need for a reducing condition in the second step. Only water is sufficient. The result is the breakage of this triple bond and the formation of carboxylic acid for internal carbons and carbon dioxide for terminal carbons. For the case of propyne here, this bond here breaks and this component, which is monosubstituted, forms the acetic acid, and this component here, which contains the terminal carbon, becomes carbon dioxide. If an internal alkene is used, then 2 equivalents of carboxylic acid is expected. Basic potassium permanganate followed by acid workup also leads to the same result as ozonolysis.